So I'll just give a brief intro for Vania. Vania is a PhD candidate under my supervision. She's been at UBC since September 2019. Vania completed a Master of Science at the University of Conception in Chile in 2015, and in 2010 completed her BSc in biology at another Chilean university, the Austral University. And so Vania's been in Canada for a little while, like since 2017. She started PhD studies at SFU, but then moved over to the Oceans and Fisheries program at UBC when it started in 2019. And Vania's holding a scholarship awarded by the Chilean government. There's a National Commission for Technological Research under the Ministry of Education. So Vania has held that scholarship. And Vania's taken a lot of graduate courses in quantitative analysis. I've offered quite a few. And in these courses, Vania's been amongst the most skilled and advanced in computer programming. Is just really incredibly impressive what she can do in terms of computer programming. And if I type in a bug when I'm typing something on the screen, she's usually right on it. Hey, you got a mistake there. So it's great to have her in the class, and her term project, she's among the most ambitious of students in that work, selecting to do really complex analyses with a lot of data. So it's really impressive what she's been doing. And so the analyses that Vania is presenting today, she began in her term project in the course decision analysis course I was teaching last autumn. So with that, I'll put it over to Vania.
Okay, thank you very much, Murdoch, for the introduction. Good morning, everyone. So I'm going to talk today about stock assessment models. Sorry, I'm going to put the pointer first. Okay, here. So I'm going to talk today about stock assessment models and Bayesian decision networks for Atlantic cod from Bay of Fundy and Scotian shelf. So cod has a broad distribution in the Western Atlantic, ranging from Cape Hatteras to the coast of Greenland. Several concentrations are found along the Canadian Atlantic coast, including those on the southern Scotian shelf and Bay of Fundy. So I will also refer to this stock as NAFO division for X5Y, because this stock corresponds to the management division for X5Y of the Northwest Atlantic Fisheries Organization. So cod from Bay of Fundy and Scotian shelf are assessed together as a single unit. However, they exhibit different growth rates. Fish from Bay of Fundy grow faster than fish from Scotian shelf. There is mixing between both areas, and fish for XP exhibit a characteristic of both growth curves, but the rate of mixing is not clear, and the mixing varies seasonally. So the majority of Atlantic cod in divisions for X5Y are harvested as a part of a mixed species fishery that include haddocks, pollock, winter flounder, and other species like redfish, for example. So cod may be considered as a choke species because the quota of other species is limited by the incidental catch of cod, which has a very strict bycatch limit. So in the past, this stock supported an important directed fishery and was caught using troll, handline, longline, and gillnet gears. But currently, due to the low biomass levels and low quota levels, only a very small amount of directed fishing take place in this management area. So this figure showed the landings of cod between 1953 and 2016 by different fleets. So an important decline of catches has been observed since the middle of the 90s. Also, catches have remained below the TAC since the middle of the 90s. So declines in abundance have been observed since the beginning of the 2000s and have persisted despite the reduction of fishing effort. So for example, here in this plot, I show how the survey biomass has declined in the last 15 years. So due to declines in abundance, this species is also limiting the fishing opportunities of other species like haddock, for example, which catch is limited by the bycatch quota of cod. So it has been hypothesized that the recovery of cod from divisions for X5Y and neighboring stocks has been prevented by increases in natural mortality of older fish. And some studies said that high levels of natural mortality may reflect a predation-driven allele effect or a predator pit resulting from a severely depleted abundance of cod and the rising abundance of gray seals. So estimates from stock assessment model showed that the southwest Nova Scotia colonies of gray seals increased more than fivefold between 2010 and 2017. So using Atlantic cod from Bay of Fundy and Scotian shelf as a case study, I wanted to explore the following research questions. So my first question is how much do the estimates of time-varying natural mortality may differ when we estimate annual natural mortality variability using multipliers or random walks? So to answer this question, I will evaluate alternative approaches to estimate time-varying natural mortality in BPA models. And I will compare the estimation performance of yearly random walks and annual multipliers to estimate time-varying natural mortality. So my second question is what covariate could help to explain increases in natural mortality for X5Y Atlantic cod? So to answer this question, I will assess the relationship between estimated time-varying natural mortality trends and some ecological covariate that could be impacting the natural mortality estimates. My next question is how sensitive are future trends in spawning biomass to different harvest rates and future natural mortality trends? So I will explore the recovery of spawning biomass under different harvest rates and hypothetical future natural mortality trends to answer this question. My last question is, can Bayesian belief networks or BVNs be used as a tool to evaluate the outputs and represent the result of fishery simulation and provide information useful for fishery management decisions? So BVNs, like this kind of graph, are probabilistic acyclic graphical models that represent the components of a system and their interrelationships, incorporating uncertainty. So BVN have been widely used in different fields. For example, they have been used to make military decisions in simulation models of conflict, also used in health and medical science, and increasingly used in ecological and environmental management and decision-making studies, such as the management of protected areas for wildlife. So, however, only a few examples exist about their use in fisheries management decisions. So, one classic example of the use of BVNs in fishery management is the work of Quick et al. 1999. So Quick et al. Used as a case study the Baltic cod, and they analyzed using this BVN how uncertainties in recruitment and growth and different fishing effort levels may affect cod management performance metrics like the yearly catch or the risk of recruitment failure. So to answer this last question, I will demonstrate how I use a BVN to analyze the outputs of my simulations and to explore the results under a decision analysis context. Okay, so I fit BPA models to code fishery independent and dependent data. So I use the same BPA model that Rose and Walters 2019 used for the Northern code. So the model was provided by Professor Carl Walters. And using BPA models, we avoid the typical problems faced when estimating time-varying natural mortality in forward catch-at-age model. So like the correlation between M and vulnerability and recruitment parameters. So in the VPA, vulnerability is derived and not estimated as a free parameter, and stiffness or the compensation ratio are estimated outside the VPA model using the outputs of the VPA. So here I have two model versions. So in the first, the natural mortality is estimated as annual multipliers. So this is model MM1 and MM2. And in the second version, M is estimated following a random walk process in models MRW1 and MRW2. So the only difference between MM1 and MM2 is the mean prior that I use to estimate the initial natural mortality of the model. And same here, the only difference between MRW1 and MRW2 is the mean prior that I use to start the estimation of the initial natural mortality. So these are the equations that I use to estimate time varying M. So I assume log normal variation for the annual multipliers. Here in MT, I for the process error of the random walks. So these plots show the BPA estimation of the model MM1, which use annual multipliers, and the model MRW1, we use the random walks to estimate M. So the first plot here are just the observed catch in kilotons. In the second plot here, you can see the harvest rate in black, here with error bars in both models. And in gray, you can see here the estimations of natural mortality for model MM1 and for model MM2. Sorry, MRW1. So you can see that the median estimate of natural mortality are higher in the model that estimate M using random walks in comparison with the model that estimate natural mortality using annual multipliers. So here in the third plot, you can see the fit of the survey biomass. So there is an important decline in the last 15 or the last 20 years in the biomass of the survey. But you can see that there are no big differences between the fit of the model that use annual multiplier and the model that use random walks, at least in the fit of the survey biomass. In the last plot here, I have the spawning biomass estimated by this model by M1 and the spawning biomass estimated by the model MRW1. And here in red with error bars, you can see the estimation of recruitment in millions. So here in this plot, I'm comparing the four models. So in red, you have MM1, in light blue, you have MM2, then in green, MRW1, and in dark blue, MRW2. So the first panel here is the spawning biomass, then I have the recruitment, then the harvest rates, and then the estimations of natural mortality for each model. So the model that use annual multiplier to estimate natural mortality predicted larger biomass, larger spawning biomass before the 1990s, but lower levels of spawning biomass in the recent years, in comparison with the models that use random walks. Something similar I observed here in the recruitment. So the recruitment was larger in model that use multipliers in the past, but it had lower levels in the recent years. Also, there were some differences in harvest rate. So, for example, the models that use multipliers, MM1 and MM2, predicted larger harvest rates in the recent years, and the model that use random walks predicted lower harvest rates in the recent years. Here in this plot, you can see the estimation of natural mortality, the comparison between both both models. So here you have the model that use random walks, and here in red and light blue, you have the model that use random multipliers. So in general, the model that use random walks predicted larger natural mortality values in comparison with the model that use multipliers. But here in this period, the natural mortality estimated by random walks was higher in comparison with the model that use random walks. There was a few differences between MM1 and MM2, and also between MRW1 and MRW2. But these differences are more at the beginning of the estimation and can be explained by the difference mean prior that I used to estimate the initial natural mortality, because that is the main difference between both models. So here I plot the fit of the Henriquez to recruitment relationship for MM1 and for MRW1. So the models using random walks predict a more compensatory recruitment than models using multipliers. Here in the second set of plots, I am showing the standardized residuals of each model. And here in this table, I show the parameter estimation of each model, the recruitment parameters. So I found important differences in the estimation of the productivity parameter A here. For example, the models that use a multiplier predicted a lower value of the parameter A and higher value of the parameter A. Here, the model that use random walks. Something similar was observed with the density-dependent parameter, the dependence parameter B. So it was lower here in MM1 and MM2 and higher in MRW1 and MRW2. And here so here I plot the spawning biomass versus the natural log of the recruit per spawners. So here I put in color the more recent years. So we can see that the last year, for example, 2014, 15, and 16, we can observe a decline in the natural log of recruit per spawners as the biomass decline. But it's important to mention here that there are no negative values of the natural log of recruit per spawners. So apparently, no recruitment failures had been observed in this stock. Okay, so as I showed before, there is an increase in natural mortality starting in the middle of the 90s. So I was interested in exploring what covariate could help to explain those natural mortality trends. So I explored the relationship between M estimate from the different BPA models. So here in each box, I have each BPA model. And I plotted together with the abundance of gray seals and also with the haddock recruitment. So I explored different covariates. For example, I explored also the spawning biomass of herring, but I found significant relationship between seals and natural mortality and haddock recruitment and natural mortality of cod. So, okay, so why I'm using this covariate? So, well, first, gray seals have been described as one of the main predators of cod, and also their abundance has increased significantly in the last years. On the other hand, haddock and cod show spatial overlap, showing a similar ecological need. Previous studies suggest predator-prey interaction between both species, being cod the main predator of haddock age 0. So, for example, when strong recruitment events occur, for example, like this strong recruitment of haddock in 2013, this ecological interaction between haddock and cod can be more important due to stronger density-dependent mechanisms that may regulate the population dynamics. So I fit some linear models to assess how much of the predicted natural mortality of each BPA model could be explained by the abundance of seals and by the recruitment of haddock. So I found a significant relationship between natural mortality of M predicted by the different models and the seals abundance and the haddock recruitment. So I apply a multivariate linear regression, including the abundance of seals and haddock recruitment together, to try to explain the natural mortality estimate of each model. So for example, in models that estimate time varying M as annual multipliers, like MM1 and MM2, the abundance of seals and haddock recruitment together explain around 40% of the predicted natural mortality. And the models that estimate time varying natural mortality using random walks, like MRW1 and MRW2, the abundance of seals and haddock recruitment together explain around 60% of the predicted natural mortality. So as I wanted to project the code dynamic into the future, I needed to decide what natural mortality level to use for future projections. So I simulated different future trends of abundance of seals and haddock recruitment to predict natural mortality values for the future projections. So for example, in this case, in the case of seals, I use as initial abundance for the projection, the abundance of seals of 2016, the mean value estimated in the stock assessment of seals from Scotian shelf. Then I simulate 6,000 slopes with uniform distribution from minus 0.5 to 0.5 to simulate increases or decreases in seals abundance. And then I incorporate simulated log normal errors to the trend. So here, you can see the simulated trends of seals in red and the simulated trends of haddock recruitment in green. So after I simulated the trends for seals and haddock, I used those trends to predict the natural mortality that I will use for future projections. So I predict the natural mortality using the multivariate linear model that I presented before. So this plot shows the historical natural mortality trends estimated by the different BPA models before the red line. So here is the historical M. And then here, after the red line, you can see the natural mortality values that I used for future projections. So here you can notice that the simulated M trends for projection were similar in MM1 and MM2 and were lower values in comparison with the values that I use in MRW1 and MRW2. So I projected the code dynamic under 11 different harvest rates. So here, and different scenarios of future M. So the harvest rate were multiplier of the terminal harvest rate estimated by the BPA models. And the future natural mortality trends were those that I predicted with the linear models and the simulated trends of seals and haddock. So these are the models that where time-varying natural mortality was estimated as annual multipliers. So here the black lines separate the historical prediction from the BPA models from the projections. So under MM1 and MM2 models, it is possible to predict a recovery of the spawning biomass depending on the harvest rate that is applied. So for example, the MM1 model predicted applying a harvest rate lower than 60% of the current harvest rate could allow the stock to recover in the long term and reach spawning biomass levels close to those observed in the past. Now the model MM2 is more pessimistic and predict that applying harvest rate lower than 40% of the current harvest rate could allow the stock to recover in the long term and reach spawning biomass levels close to those observed in the past. So model MM1 predicted a little bit larger recruitment than model MM2 and also predicted larger catch levels in comparison to model MM2. Now here, there is a comparison of a model where time-varying natural mortality was estimated using random walks. So here, the black line separates the historical prediction from the projections. And none of these models allow the recovery of the spawning biomass in the long term. Also, you can see here that the recruitment levels are very low in both models, and almost there are no catch predicted for the future. It can be explained by the larger M values predicted to project the future cod population dynamic used under these scenarios of random walks. So after performing all the simulation and projections, I incorporate my results into a Bayesian belief network to assess how the structural uncertainties may affect code performance metrics, utilities, and the possible consequences of different harvest rates. So this CDN includes one decision node here called policy in red color. So this policy node includes the 11 harvest rate that are multipliers of the terminal harvest rate estimated by the different BPA models. So the harvest rate go from 0 to the terminal harvest rate. So this VDN also contains a parent node here in blue. So this parent node don't depend on other nodes. So for example, the node model, which includes the 4 models that I mentioned before. Also the slope of haddock and the slope of seals are also parent nodes. So these nodes were the slope values that were used to simulate the future trends of seals and haddock, and that were used also to predict the natural mortality values that I assume for future projections. So the VDN also contains a child node that depend on the parent node. For example, here the store recruitment parameters A and B from the Recurrent model, which contains the parameters used to project the recruitment of code into the future. The node average M and change of average M are also child nodes that contains the average M value used for projection and the average annual change in natural mortality in the projections. So this set of nodes here in yellow include the performance metrics of the model. So the first one was the average catch, the second one, the annual variability. Then the last two are different measures of spawning biomass depletion. The next set of nodes, these nodes are the utility nodes, which represent the utilities in dollars generated by each performance metric. And the final node here in green represent the multi-attribute utility function that depend on the utility generated by the performance metrics and was defined based on the landing price per kiloton of Atlantic cod. So in the BVN, there are conditional probabilities linking the parent node with the child node, and these probabilities are represented by these arrows. You can see some values associated here to each discrete level of each node. So for example, here in the node model. So these values represent the probabilities associated to each discrete level. And in that node, for example, all models are equally likely. So for example, when evidence in a node is specified, for example, if I assign probability 1 to MM1, the effect will propagate all over the network, and the marginal probabilities will be estimated using the Bayes theorem. So using the VVN, I wanted to explore what would be the optimal harvest rate if I assign the same credibility to each model. That means all models could be equally likely with a probability equal to 0.25. So under those assumptions, I analyzed what harvest rate generate the largest utilities. So the VVN showed that the harvest rate that generate the largest utilities are 60, 70, or 80% of the terminal harvest rate. So remember that the terminal harvest rate is the harvest rate of the last year of the VPA model. So using those harvest rate, 60, 70, and 80% of the terminal harvest rate, I plot the catch level generated by each harvest rate and the probabilities associated to each catch level. So here in the x-axis, you can see the harvest rate, and in the y-axis, you can see the probability of getting different catch levels. So we can see that the three harvest rate generated similar catch level with similar probabilities. So the highest probabilities are associated to catch levels between 0.2 kilotons and larger than 1.4 kilotons. And the second plot here shows what spawning biomass depletion levels are generated by those harvest rates. So we can see that in most of the simulation, depletion levels will stay below 0.1 with a probability around 0.4. So here, please note that the depletion is calculated as the ratio between the spawning biomass at the end of the projection in 2046 and the spawning biomass at the beginning of the fishery in 1948. So I tested if under the hypothesis that all models are equally likely, it is possible to observe a recovery of spawning biomass. So this plot shows in the x-axis that harvest rate 0 and the terminal, show the harvest rate 0 and the terminal harvest rate. In the y-axis is a probability associated with each depletion levels of spawning biomass. So we can see that a zero harvest rate still have a probability larger than 0.3 of generating depletion values less than 0.1. But also it showed that probability is larger than 0.2 of generating depletion values larger than 2. The chances of recovery under the terminal harvest rate are minimal, and there is a probability larger than 0.4 that the depletion of spawning biomass will stay below 0.1. So the BVN also allow us to assign different probabilities to each model to illustrate what happens if we put all the evidence in one model. So for example, here, what happens if I put all the evidence to model MM1. So in this case, I assign a probability equal to 1 to this model. And under this scenario, the BVN showed that the harvest rate that generated the largest utilities was the 60% of the terminal harvest rate. So here I assigned different probabilities to each model. So for example, first I assumed that model MM1 was the correct model. So I assign a probability equal 1 to that model. And under that scenario, the optimal harvest rate was 60% of the terminal harvest rate. Then I assumed that model MM2 was the correct model. And under that scenario, the optimal harvest rate was 70% of the terminal harvest rate. Then I did the same for the random walks model, and in those scenarios, the optimal harvest rate was the terminal harvest rate. So in the first plot, I showed the level of catch generated by each model. Model MM1 and MM2 have larger probabilities of generating larger catch levels. So in comparison with the models MRW models. So here, for example, there is a large probability of generating a lower catch level between 0 to 0.2 kilotons. So in the second plot, I illustrate the level of depletion of spawning biomass generated by each model. So here also the models MM1 and MM2 have larger probabilities of generate less depleted biomass in comparison to model MRW. So these models, MRW1 and MRW2, keep the spawning biomass at very low levels with depletion values less than 0.1 in most of the simulations. So the VDN allows us also to assess what will happen if the future trends of seals and haddock change. For example, if these trends increase or decrease. So here, only as an example, I will demonstrate what happens if seals decrease in the upper panel or increase in the bottom panel in terms of catch levels. So under the scenario seals decrease, we can observe a high probability, around 0.9, of obtaining larger catches, larger than 1.4 kilotons, but only if model MM1 or MM2 are the correct models. So the catch levels obtained if MRW1 or MRW2 are the correct model are still very low, even if seals decrease. Under the scenario seals increase here, the probabilities of getting larger catches decrease in all models. So for example, here in MM1, we can see that the probability of getting catches larger than 1.4 kilotons decreased to 0.6 in comparison here with this plot where the probability was around 0.8 or 0.9. So here I plot the response of the spawning biomass depletion to changes in seals trends. So under the scenario seals decrease, we can observe a higher probability of recovery of spawning biomass with depletion levels between 1 to 2 in the scenario MM1, and depletion levels between 0.5 and 1 in the scenario MM2. On the contrary, MRW models show that even under the scenario seals decrease, it is not possible to expect a recovery of spawning biomass. So we observe here a high probability of getting depletion values less than 0.1. Under the scenario seals increase, the chances of recovery decrease in MM1 and MM2. And in MRW models, the results are very pessimistic, with a probability larger than 0.9 that the spawning biomass depletion will be at levels less than 0.1. So the last part of this simulation work was to estimate the value of information. So decision theoretic models like BDNs can be also studied with respect to the value of information, which allow us to understand which types of uncertainty in the system could most deserve further studies. So the value of information shows us how much the new information could improve the performance of decision making and what is the maximum price that should be paid for the new information. So the value of information assigns a numerical value to obtaining a particular form of new knowledge. So most often the value is understood as a measure of the economic value of information. But there is no need to be so restrictive, and any quantitative measure of utility can be used. For example, the number of fish landed or the perception of happiness. So I use the decision table to illustrate the calculation of the value of information. So here, for example, each column represents one model, assuming that each model could be equally likely. And each row represents the different harvest rate that I tested in my simulations. So the column here, E average catch, is the average yield average across the 4 models, assuming that each model could be equally likely. So in this decision table, we can see that MM1 and MM2 are the most conservative model. So 70% or 80% of the terminal harvest rate are the best harvest rate if MM1 or MM2 are correct, because this harvest rate generated a larger average catch. So the models MRW1 and MRW2 are less conservative, and the terminal harvest rate is the best policy option if MRW1 or MRW2 are the correct models. So the best non-adaptive policies are 70% or 80% of the terminal harvest rate, which generate the maximum expected value in terms of catch, given an average performance of 1,059 tons across all the models. So the value of information was 20.2 tons per year, which correspond to 32,000 Canadian dollars per year. So this value represents the difference between the expected value of the optimal decision given perfect information about the models and the value and the expected value of the optimal decision given no information about the models. So the value of information was calculated assuming a landing price of cod of $1,587 per ton. The value of information was a very low value in economic terms, but it happens because the current value of the fishery is very low due to the existing biomass levels and also due to the current low quotas. So in conclusion, estimating time-varying natural mortality using random walks generated the highest values of natural mortality. So models that estimate time-varying natural mortality using random walks may overestimate the natural mortality. So time-varying natural mortality estimate using random walks fit the actual peaks or the decline in M not on time. So for example, M estimate start to progressively increase or decrease several years before the actual peak or the drop of M occurs. Other multipliers allow M to change rapidly over time, so the actual natural mortality estimate can be detected on time. A projection of the population dynamic of cod showed that only those models that estimate M as a non-multiplier predict recovery of spawning biomass in the long term. Finally, the VBN showed that harvest rate between 70% or 80% of the terminal harvest rate could generate the larger utilities in most of the scenarios. Also, VBN showed that under structural uncertainty, for example, where all models are equally likely, fitting at the current harvest rate generates the highest probability of keeping the population at very low biomass levels. As I mentioned before, the value of information was a very low value in economic terms, and it happens because the current value of the fishery is very low due to the existing biomass levels and the current low quotas. So it's important to invest resources in learning more about how to model time-varying M for Atlantic cod, so better utilities could be obtained and better management could be implemented in the long term. As this species acts as a choke species, limiting the fishing opportunities of other fisheries, for example, like haddock fishery, it is important to make effort for its recovery. So I want to say thank you to Jung Wang from DFO. She provided me the data for the stock assessment models. I also thank you to Professor Carl Walters, so he provided me the VPA models, and thanks to my supervisor. Thank you very much.
Great, thanks, Vania, for a really excellent talk. Do we have some questions for Vania?
Oh, nobody's going to jump in. I'll ask her one. It's Carl.
Hi, Carl.
And yeah. One really key thing when you have a big predator like the seals as a potential mortality agent is to try to cross-validate the mortality of the mortality estimates based on correlation with direct mortality estimates that you can obtain from the seal numbers and their probable consumption rates and relative to the biomass cod, just to see if they could be eating enough to cause any part of the observed mortality change. Did you try to do any of that kind of independent cross-validation?
No, I just try to, for now, I just try to assess the correlation between natural mortality of cod estimated by each model and the abundance of seals. But that was all the correlation analysis that I did for now, yeah. But I need to improve that because I'm still working on that. So I need to do more analysis to get better, a better idea.
So one more question.
Okay.
The signal in the data about changes in natural mortality rate basically comes entirely from the survey age composition data,
Yes.
which give direct estimates of survival rates from year to year for fully recruited fish. When you just look at those survey catches at age, catch rates at age, do they show relatively clear changes, particularly the disappearance of older fish?
Yeah, I observed
in
that.
the times of high mortality?
Yeah, so I observed that, for example, in the last year, there are almost no fish of age, I don't know, after age 8 or 9, there are very, very few fish of that age, of older ages, yeah, in the catch at age data from the survey, yeah. Yeah, but I'm not estimating the natural mortality by age group right now. So just I'm estimating just the natural mortality for each year, not for age group. So I haven't estimated the natural mortality of older fish yet.
No, you don't want to try to estimate it by age. That's hopeless.
So.
But you should see a really clear
Yeah.
average across ages increase and decrease in the ratios of catch rates in successive years. It sounds like you got that. So the natural mortality variation is real. The issue is just what's causing it.
Yeah.
So Vania, just a question / comment. So this is just a very southern extent, at least in terms of Canada, cod stock. And that there are a bunch of other cod stocks a little to the north, like Gulf of St. Lawrence, and George Roach just presented the Grand Banks sort of analysis. And they also have time varying M. So I think it probably would be interesting to look at the patterns. Like there are increases in M estimated for those stocks, but in your assessment, there's some really large swings, like the periodicity is maybe 6-7 years or something like that, and you're not explaining those really big swings up and down. So there's still a lot of unaccounted for variation. It'd be interesting to hypothesize, is that just an artifact of something that's not real, or is that potentially real? Perhaps it's really clearly shown in the survey data. But then to look at other stocks, it'd be interesting to look at the other cod stocks where time varying M has been estimated. And okay, from the Walters and Rose, they use the multiplier sort of approach, which kind of doesn't have the residual effect of this the other approach, where you're having this random walk. The random walk effect sort of can create artificial covariation or autocorrelation. So it'd be interesting to compare these estimates. Have you actually had a look or comparison between your estimates of time varying M versus time varying M and the other cod stocks?
No, I haven't yet. No, I review the other trends, but I haven't made like a correlation or a comparison between those estimates and my estimate. Not yet. I will.
Okay, thanks. So do we have a few additional questions or comments?
I had a couple of comments, Murdoch.
Thanks. Go ahead.
So one thing that I really found interesting was in your belief network comparison where you showed showed how the harvest rates, like if you didn't have any information on which model was, you could put faith on, and you gave equal weights, and the final conclusions were very similar, is what I felt in terms of harvest rates.
Oh, yeah.
That I found really interesting from a management perspective. One question there was the terminal harvest rate you're taking, that is relative to the terminal harvest rates in each of the models, right? So
yes.
Yeah, so although the catches are much different, you know, like in the harvest rate term, it is useful, but if you think of it from the perspective of prescribing a tag, then it becomes difficult. But still, you know, like from a harvest rate perspective, that was good, I think. I just had, I mean, I found this talk very interesting, and like the final presentation into BBNs, I found it really, I really liked it, but what I was interested in more is like a little bit more about the models also. So I had a couple of questions. So one was with regards to recruitment. Like you had these, you showed the fits to the survey biomass. Like, have you had a chance to compare the recruitment estimates with the survey? I mean, do you have a survey for the younger ages? Like, could you show a comparison of recruitment estimates from the models against the survey?
Oh, I don't have that right now here, but you mean if I have so these are the recruitment estimate here, the recruitment fit of the model, and here I have the recruitment estimate. So these are coming from the VPA, so the H2 from the VPA, like an output of a VPA. Yeah.
Yeah. So I was curious if, I mean, if it would be possible to compare the VPA outputs with like a survey of H2 survey. I don't know, H2 or H3 in the survey.
Oh, okay. You mean the fit of the H? Yeah, I have that. I didn't put that here because it's a lot of information, but I compare. Yeah, I compare the estimate of the H composition against the observed catch age from the survey. Yeah, I did that. Yeah, but I didn't put that here in my presentation because it was so many plots. So yeah.
Yeah. No, I was just curious. I mean, if like if fits like that would like could provide you something to, like, instead of assigning 0.25 to each parameter, if there is some information in the fits that could be used to assign a different probability to the models.
You mean to the
yeah,
BBN? Oh, I see. Okay.
Like can you use some diagnostics from the models to give you probabilities in the BBN? So that's the.
Oh, I didn't explore that, but that is a good idea.
No,
yeah, I could try.
That isn't going to work.
No, why not?
No, it won't, because she's already fitting to the survey recruitment estimates. They're the younger ages in the survey data.
Oh,
and but the absolute catchability coefficient for the survey isn't known. So you can't use differences in the absolute values of recruitment between the scenarios. As there is no absolute value for recruitment estimate that you could use.
No, I was just talking about diagnostics in general, and not only that, like it would be good to see how the models compare, like just a fit comparison. I mean, in terms of recruitment trends, I mean, do you see, I mean, are the residuals like IID residuals across all the 4 models, or do you see overestimations or underestimations in one part of the series? Just curious what that looked like. This is not a question, this is just a curiosity. So in the multiplier, the natural mortality multiplier model, are they, like, how are they connected between years? Is there no connection? Are they independent, the multipliers?
Yeah, the multipliers are independent. Just random walk depend from the previous year. Yeah.
So there is no connection, like there is.
No, I assume
is there a penalty or something?
Log normal variation. Yeah, for the multipliers. Yeah, there is a penalty. Yeah, but there are no related to the previous year, for example, like in the random walk.
In the random walk, okay.
One diagnostic I think maybe answers your question. I don't think Divya has done yet. Is we've done it, for example, with herring data, and that's to go in and directly estimate survival year-to-year survival rates from the age-specific catch per unit effort. So that's the relative abundance at age. And what you find in like with the herring is you get negative values for some time, some years. There actually appear to have been gains in numbers from one year to the next rather than a decline or decay or survival thing. And that's an indication that something's wrong in the model structure along the lines you're talking about. Like that could, what we, in the herring case, we think is probably due to incorrect specification of the maturation schedule combined with actual movement of herring between areas. So it's a warning that there's a mixing process when we get negative natural mortality.
Oh, okay. Wow, interesting. Like these questions are all curiosity questions, Vania. I'm not trying to attack your work at all.
No, it's okay.
Another question. I mean, I guess this is for Murdoch, really. Murdoch, if you remember in the model that you did for trout and kokanee, the Kootenai Lake model, there was a structure of M. I don't remember it very well, but there was a structure where like
There's a
M
functional response. There was a functional response.
Functional response. Which was dependent on.
That's partly dependent on the L infinity of the kokanee.
Yes. But also the natural mortality on kokanee was dependent on I think transparency or something like that. Murdoch, was it? Like there was this. It was a covariate dependent natural mortality. I was curious. I mean, Carl. I mean, like, would you think like bringing that kind of structure into the VPA? I mean, asking VPA to like giving VPA the data on seals and haddock and see if it can estimate that. Like
you mean like including as a functional response inside the VPA or no?
No, not really, but just as a covariate, like a covariate that varies over time, and you have a parameter attached to the covariate. I can maybe send you the paper that I'm talking about and see and just think about whether that's a feasible approach or not. But
maybe I think I understand. What are you telling me? So you mean like, for example, to include a covariate for the estimation of natural mortality inside the VPA model, right? Something like that?
Something like that. So then in the projection, you don't have to make this assumption that because now in the projection you have this multivariate model which you are basing to project your M's as to it's a bit tenuous as to see like, okay, you have this parameter from the multivariate model which is influencing how field effect is being modified. So that's the reason I said that. All right, thank you. That's all.
Thank you, Divya. Thank you very much.
One thing we've done to follow up on what you're saying there with the herring models is we've actually used seal abundance to calculate an estimate of the total herring consumption for each area for each year, changing with the numbers of predators out there. And then we actually have included that as a catch in the VPA.
In the VPA, okay.
Right.
That's Carl, just curious, when you do that, I mean, do you get we have been doing something similar here, and just in terms of magnitude, it's like very different. Like, do you get concerned about, I mean, like the bioenergetics, and is it really like, are the values comparable to, for example, when you use a bioenergetics model for consumption, there's considerable uncertainty in the estimation. So is that comparable to like a fisheries catch value where you have a lot more faith because it is much more directly collected data? So have you come across concerns like that?
Sure. You always do this with a range of estimates for anything like that that's uncertain. But what comes out in herring cases is that when you put any kind of reasonable value on the likely consumption by sea lions, mostly actually of herring, it ends up, and then put that in as VPA catches, the M trend from the assessment goes away. And it goes away for a pretty wide range of estimates of the absolute consumption per seal. So that just strengthens the argument that most of the trend, at least with herring, is
from the
sea
seal.
lion,
Yeah.
from the sea lions. Yeah.
And that's a VPA, or?
Yeah.
That's very interesting, Carl. Thank you.
Thank you very much, Vania.
Okay.
Thank you very much, Vania, for a really interesting talk. And thanks everybody for participating and also for the great questions.